I'm super excited for our morning's keynote today. Today we have Josh Saxe, who actually has his wife Senia in the audience today. So we're happy to have a family event for the first time at CAMLIS. I'd like to just introduce Josh, who's a well-respected researcher, almost needs no introduction to our community, a researcher and a friend. Josh Saxe is a senior staff AI scientist at Meta, where he leads Meta's efforts to integrate security into its large language models and protect them from application-level cyber attacks. Before joining Meta, Josh served as chief scientist at Sophos, principal investigator on multiple DARPA programs at Invincia Labs, and led machine learning security research at Applied Minds. Joshua, with co-author Hilary Sanders, co-authored the book Malware Data Science, published by No Starch Press. He's also authored many peer-reviewed scientific publications that have affected lots of us in this community, and he holds more than 20 patents. But interestingly, Josh started his career in community organizing and made his way eventually into the hacking scene and eventually into data science for systems and network security before running DARPA programs at Invincia. This transformation will not be surprising for those that know Josh. He is a self-described autodidact. I looked that up. It means somebody who teaches himself things. See how that works? He maintains a disciplined humility, which allows him to be a learn-it-all rather than a know-it-all. This may be partly why he has mastery in diverse interests that range from classical jazz piano to program analysis to building exceptional research teams. Josh is a prolific speaker. He has been the go-to speaker in machine learning and security ever since I've been in this over a decade. Josh's impact over the years has been remarkable, with co-authors, many of whom are present here today. His papers on malware classification since 2012 drove a revolution in malware classification using machine learning at a time when it was considered mostly impractical. I've personally benefited from this and Josh's fresh foundational thinking and his thoughtful humility when he's debating research questions. One of the secrets to being a great researcher, I think, is being able to anticipate the hard problems. And Josh excels at this. He can seemingly see around corners. He saw the utility of machine learning for malware classification, as I mentioned, when it was impractical. He saw the emergent utility of language models when I was still very much a skeptic and a naysayer. Few have this uncanny ability to see around corners. So I would encourage you to listen up today as Josh gives this morning's keynote that is aptly titled, "You'll Never Guess What Happens Next." Please join me in welcoming our morning keynote speaker, Josh Saxe.
Okay, so I'm Josh Saxe. So my talk is entitled, "You'll Never Guess What Happens Next, Acting to Ensure AI Benefits Cyber Defense in a Decade of Technological Surprise." I want to thank everyone I've worked with over the past few years. I listed a bunch of authors. I could probably list a lot more on papers that I've been on over the last few years. So it's a really big team that's behind the talk that I'll give today. I'll give a lot of spicy opinions and I'll take responsibility for those. But thanks to all my colleagues, both at Meta and at Sophos before that, for your inputs to this talk. Yeah, so actually Hiram covered a lot of this stuff, but so my background is in, I started out in the sort of late 90s hacker youth culture in high school. That's when I did my first work in sort of network security and memory exploitation and that kind of thing. And then I worked for about a decade in national security on DARPA and NSA funded applied research programs in AI security. Then I've been in the commercial space for, 7 or 8 years. I worked for security vendors. So I was at Invincia building AI security there, and then we got acquired by Sophos, and I was there, and I've been at Meta working on mostly on Llama for the last couple of years. That's me and my family. My wife's here watching me give this talk, and we live in Kansas, and did a bunch of things other than this field for a while before getting back into tech in my 20s. Okay, so here's the argument I'm going to give in this talk. Is there a way to show the slides on this display up here? If there is, that would be helpful. Otherwise, I'll just keep looking behind me. Okay, thanks, Lauren. Okay, so I think that we're incredibly lucky to be working in AI security right now. I think it's easy to forget amidst all the sort of stress and pressure that many of us feel given what's happening in AI. But I think it's quite likely that we have the opportunity to shape one of the pillars of technology that's going to affect the rest of the century right now and make it and place it on a secure foundation. I think what we do now is going to be really consequential because we'll get to make choices that have enormous downstream impacts as AI gets adopted. We're sort of at the base of the adoption curve, and I think we're about to hit sort of an exponential sort of phase in that adoption curve. But I think we also have very little certainty around what's going to happen next. The history of AI is really that's okay. Don't worry about it. The history of AI is really the history of technological surprise, which I'll argue. And so we have this dilemma that we have to act without knowing what's going to happen next. So here are a bunch of sort of surprises that we've experienced, that those of us who've been around for a little while have experienced. So up until around 2012, computer vision was an interesting academic discipline with a few application areas in industry. But it mostly didn't work, right? Like if you asked a computer vision model to detect objects in the open world, it usually failed. And then suddenly it worked. And that was a surprise to those of us who were around at that point. Deep learning, which operates well in continuous domains, suddenly working in discrete domains, learning syntax and semantics and language was a huge surprise. I remember when I first saw an LSTM spit out semantically incorrect but syntactically correct code, and that was a huge surprise. Self-driving cars not working when they were supposed to by now have taken over the world, and then working later. Gradient-based attacks, were a hot research topic for a long time. Never really appeared in the wild, at least as far as I know. And then prompt injection appeared out of nowhere, in the wake of ChatGPT, and is now a huge research topic. And then ChatGPT was obviously a huge surprise. Basically, I think that the way we need to approach our fields is with a kind of simple algorithm in which we stay tightly bound to evidence, and in a sort of infinite loop, update our beliefs based on evidence, make sure we're not fooling ourselves, which I think happens all the time, and I'll illustrate that later in this talk, and then just take the next small step. Now, this might seem obvious and easy to stick to, but I think we fool ourselves in all sorts of ways in our fields, and I think it's easy to get caught up in narrative and priors, and actually not update on evidence. Okay, so here are some ways that I think we fool ourselves, and I've fooled myself in modeling work. A typical AI security paper that proposes the machine learning approach will claim that it works better than baseline approaches. But I think what we often leave out is that we grid searched our hyperparameters, much more intensively than the baseline approaches. Like I certainly have been a culprit of this. Oftentimes a paper will start out with a flashy claim, like AI can automate hacking, but without really highlighting the conceits that it makes around the toy environment in which those experiments were conducted. There's this t-SNE example, which I like. This is like a hobby horse of mine, bashing t-SNE. But so if you look at, oftentimes I think what happens with t-SNE, like how many of us have plotted data with t-SNE, right? So I think oftentimes what happens with t-SNE is you have like a 10,000 dimensional data set, you plot it, and the plot doesn't look quite right? So then we tweak some hyperparameters, and we sort of rinse and repeat until we get a projection of our data that confirms our priors, right? And so this plot on the right just shows an example of plotting a t-SNE plot, 6 times, and depending on how you tweak the perplexity hyperparameter, you can argue that your data is uniform or Gaussian or a whole variety of things. And I think this happens all the time. I think it's a sort of microcosm of a larger phenomenon that happens in our research practice. Funny, this was supposed to be animated, and it's not. So hopefully you guys will understand this slide. But basically, okay, so I think that the larger version of this can be located in the way that we think about deep learning models and what's actually going on inside of them. So I think that oftentimes, because deep learning models are opaque, they're just sort of Rorschach tests for our prior beliefs about what they actually mean. So for example, if you look at the discourse on Twitter around the nature of large language models, you've got luminaries in our fields, all of whom I really respect, right? Simultaneously arguing these models are stochastic parrots, they're slightly conscious, right? This is an actual position held by some super smart people in our fields. that they can't plan and reason, that they can, right? And I think that this discourse usually isn't really evidence-based, right? I think it's oftentimes what you see in AI discourse and AI security discourse is really folks arguing ideological positions that are pretty unmoored from actual empirical evidence. And so I think like the most extreme example of that are statements like this existential risk statement that came out in the wake of ChatGPT. So a bunch of people who've been idols to me and who I really respect signed this statement, and the whole statement is mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks, such as pandemics and nuclear war. So the idea is that we should be as worried about AI as we are about nuclear weapons. I think that's interesting. And the people on this who signed this, like Jeff Hinton, and there's multiple Nobel Prize winners who signed this, like Demis Hassabis and Jeff Hinton, who are way smarter than me and who I've respected for a long time. But I think this is an example of discourse that's not based also in evidence. And I think this is actually, I think statements like these are part of a long history of statements that weren't really rooted in evidence. Like, so for example, Herb Simon, who was one of the founders of AI in the post-war period, said that machines will be capable within 20 years of doing any work a man can do. And he said this in 1965. Marvin Minsky, another one of the founders of our fields, right, said within a generation, the problem of creating artificial intelligence will be substantially solved. And he said this in 1967. And then Elon Musk, made a similar statement about AI risk, supposedly by 2024 in his statement, we would be seeing, serious risks from AI. And I would argue that we haven't seen them yet. So I don't think the problem is that these folks aren't super brilliant. I think there's a problem with the structure of the discourse in our field that can sometimes unmoor us from empirical evidence. So here's like another statement of my thesis. I apologize for all the mid-journey and ChatGPT generative right here and the misspellings. But so how many people have heard of a OODA loop? So there's a lot of folks from the defense community here, but I'll explain it for those of us who aren't familiar with this sort of cognitive model. So OODA stands for Observe, Orient, Decide, Act, and it comes from the psychology literature around designing like fighter plane cockpits. And the idea is that we can model the state of mind of a fighter pilot who's engaged in like a dogfight as a state machine in which they are always observing the phenomena in their environment. So for example, the enemy fighter planes, orienting towards the phenomena that are important, for example, a plane that might be approaching the fighter pilot, deciding what to do next, maybe just turning the plane slightly to the left, and then actually taking that action, right? And I think that given the uncertainties in our fields and the sort of how often we're surprised technologically in our field and how often things change, we need to be in a kind of OODA loop as a community. Okay, I'm just gonna put this. This is just sort of a kitten break to stop. And I'm curious if anybody, maybe I'll take a few questions if anything's not clear, or if anybody has any reactions, and then I'll keep going to the next few sections of the talk. Okay, well then I'll just keep going. Okay, so I'm gonna look back now and apply this framework, or my thesis, which is that we need to stay sort of tightly evidence-bound and not fool ourselves and spend real energy in making sure we're not fooling ourselves, to the last 10 years of AI security. So for those of you who are new to this field, very happy you're here. There was actually an attempt to revolutionize security with machine learning in the 2010s. And there was a kind of ChatGPT moment back then, I would say, and a lot of us got involved in this community during that decade. Personally, I would say I fooled myself about what machine learning could and couldn't do a lot in that period. Personally, I didn't update on evidence enough and around what projects did or didn't make sense. And I'd say I wasted a fair bit of time. And I think I could have accomplished probably twice as much as a rough estimate had I operated based on the thesis that I'm sort of pitching in this talk. Okay, so this previous hype wave started in 2012 when AlexNet came out. That moment, that ChatGPT moment, happened in the context of a computer vision competition called ImageNet, which probably many of you know about. And the way that competition worked was that like every year over a series of years, computer vision teams would enter their machine learning models into this competition and see who could solve object like image classification problems the best. And in 2012, there was this big breakthrough where AlexNet came out, which uniquely was a neural network. Like the rest of the systems were mostly support vector machines, I think. And AlexNet got a much lower error rate, so a 16.4% error rate in this competition, whereas the competing systems did way worse. Like the second best system got a 26.2% error rate. And this was like I think for the first time, or at least for the first time in a long time, machine learning was like a New York Times headline sort of topic in the wake of these results. And people were blown away by the fact that neural networks could achieve this step function result. So there was a lot of hype after that. So in the ensuing years, computer vision got better and better. By like 2015, 2016, computer vision systems were in some fairly contrived settings, I would say, outcompeting human beings at tasks like recognizing cancer and medical images. And you had leading people in our field like Jeff Hinton saying stuff like, people should just stop training radiologists now. It's just completely obvious that within just 5 years, which would have been 2021, deep learning is going to do better than radiologists. But if you look at this plot on the right, you see this is a time series of radiologist job postings running through 2021 and 2022. And actually, there's more radiologists now than there were when Jeff Hinton made this claim. But this was the kind of atmosphere. So well-respected scientists, we're making claims like this based on really pretty radical extrapolations from the evidence, and I would say there was an atmosphere of hype and not sort of staying tightly bound to the evidence. There were also, and I don't want to pick on silence here. I think a lot of us were making claims like this, but this was like a typical marketing poster in that era, around 2015, 2016. So on the right here is a marketing poster for an AI security startup, where there's sort of a tech worker who has a crystal ball. I think this crystal ball is meant to stand in for a machine learning model. And the claim is that this machine learning model can predict and prevent future cyber attacks, right? Now, this was not so different from the radiologist claim, I would say. And I was making claims that maybe weren't as extreme, but I think we're in the direction of sort of hyping up machine learning's possibilities at that time. There was also claims around self-driving cars, replacing human drivers by now, mass unemployment, AI, and then these claims around cybersecurity. This was me hyping up the AI revolution in security at Black Hat, referencing the ImageNet results, and arguing that our mission was to sort of generalize those ImageNet results to attack detection and cybersecurity. I would say, looking back, I was more bullish than I should have been. I think I was trying my best to be honest, but I was also very much attached to the thesis that AI was going to revolutionize security in that decade. And it's hard to not buy into the hype when your paycheck depends on it, which was definitely my situation. And also your research funding, there was lots of research funding sloshing around from agencies like DARPA and NSF that my team was supported by. And so I think we were just part of this overall atmosphere. Now, there were a bunch of inconvenient truths that were lurking in the background that I think many of us sort of knew around 2012 and definitely through 2016 and 2017 that I would say we downplayed, minimized, and denied in general. So I'm going to go through these. It's a fairly long list. I'll try to go through these quickly. One of and I would argue that had we stayed in a more evidence-based OODA loop, we would have recognized these faster, and we would have recalibrated the way that we were approaching our research. So one was the sort of blank slate limitation. So models in that era mostly weren't pre-trained. They didn't have models of the world. So if you went out to try to train a system to detect advanced persistent threats using Windows audit logs, typically you'd be training your models from randomly initialized weights. They'd have to learn from scratch about the world based on your sort of supervised labeled data, and this was a big limitation in terms of model performance. We had supervised learning was the main sort of game in town in that era. We were just sort of beginning to get into self-supervised learning. So unavailable labels were a huge limitation in cybersecurity, where your adversaries are actively trying to hide their labels from you, and there's lots of problems that were bad applications for machine learning because of that. machine learning was very brittle. I mean, so even now, large language models don't generalize that well out of distribution. But really, that there were. I mean, I remember going to demo machine learning models that detected like malicious URLs for customers, and like being incredibly scared that they would, enter a URL that was like slightly out of distribution because then my model would fail. Machine learning was very brittle in that era. It's also a black box, and oftentimes we need to raise alerts to analysts who have to actually understand them, and that sort of filtered out a lot of use cases. Machine learning models in that era were really shallow pattern matchers. They were costly to implement because you needed to hire people with advanced degrees who asked large salaries. And then we also were always competing with people who could just write a regex. And that was actually very hard because oftentimes you can write a really good regex or Yara rule or Sigma rule that outperforms a model that you had a bunch of hardcore ML specialists spend like 2/4 on. I had that experience multiple times. So these were all the limitations that I think we sort of, if we were in an OODA loop where we were orienting towards the important phenomena, we would have detected these limitations in our empirical results, oriented towards them, and adapted. But I think it was hard to do that given the money sloshing around, given the hype, given the research funding, and I think that was a big problem. Okay, so here's me around 2016, 2017, trying a bunch of things and sort of not orienting towards those filters. Okay, so I spent about a couple of years trying to get machine learning to automatically reverse engineer malware binaries. And I thought I had a fairly clever approach. I think we did. I mean, I did this work with collaborators, and I think we did have a fairly clever approach, which was to train a machine learning model on Stack Overflow data, and then take those models and apply them to malware strings dumps. This approach worked. We had 2 separate research grants from 2 different funding agencies that funded this work, and we published multiple papers, and we gave a black hat presentation. But we never actually, like when it came to, like when I went to work for Sophos and we actually had the opportunity to integrate models into products, like this had to actually work in practice, and it never actually worked, and so we never actually deployed it, and that was disappointing. It was that was 2 years of research that didn't have an impact, at least in a practical setting. And I think looking back, I wish I recognized that there just wasn't enough training data for this problem. We didn't have enough actually labeled malware, actually reverse engineered malware that we could train on. And ML just can't, ML in that era could not reason about programs. And ultimately that's what you need to do to reverse engineer malware. A group of us worked on a project that was funded for 2 years to detect advanced persistent threats in computer networks based on endpoint behavior. We wound up not being able to solve that problem because advanced persistent threats operate out of distribution almost definitionally, and machine learning does not operate well out of distribution. So we wound up building a behavioral malware detector instead. And I wish I'd sort of had the discernment to understand that the APT problem can't be solved through an ML model, at least not back then. I remember building this automatic signature generator tool. This is actually still out there on GitHub if anyone wants to look it up. It's called Yara ML. What it does, so the approach I took here was I trained a logistic regression model on some domain of interest. So for example, detecting malicious PowerShell. And then I had like a translator that translated the logistic regression model into a Yara signature. And this felt clever because it basically, Yara allows you, so like the sort of fun part of this project was figuring out how to encode a linear classifier into Yara, right? And so there's like sort of a weighted summation at the bottom here and a feature extractor at the top. I thought this was a really good idea, but as far as I know, nobody's ever used it. I think the issue here is that it's very hard to compete with the human brain in doing good detection engineering. So a human detection engineer can identify features, for example, in a malicious PowerShell script that are hard to change for an adversary and likely to be invariant, right, as a malware family evolves. And a logistic regression model has no model of the world and no understanding of how to do that. And I think that's why detection engineers still write their own rules. And that was, I think, again, if I'd been operating in a sort of more disciplined and more sober OODA loop around what made sense to do in the machine learning space, I probably would have recognized that earlier. Okay, so I think like the sort of OODA problem for our research community is, again, well, okay, I'll put it this way. Like, there's a space of ideas that seem amenable to security machine learning right now, right? And that space keeps changing because the technology keeps getting better. But then there's a set of filters that sort of exclude certain use cases. And we need to be, if you imagine, I wish I had a better animation here because I would have this whole space sort of morphing and changing over time. Because like when Llama 4 comes out, the space is going to change and the filters are going to change, right? Or when Claude 4 or whatever the new system is. But we need to be like, our space is changing so quickly and it's so full of hype and there's such a propensity to illusion and getting sort of inebriated with the excitement of our fields that it's very hard to stay sort of sober and focused and sort of precise around what this space looks like and where we should actually make investments. Okay, so I would say in the last decade we did discover a killer app of machine learning, and I would argue that what we discovered a bit too slowly was the detection of scaled automated cyber attacks was the single killer app of machine learning before generative AI. So put more colloquially, like what I mean by that is I don't think the problem in the 2010s era was to detect advanced persistent threats or solve sort of high cognitive load problems like malware reversing. I think the problem actually was to detect the sort of massive malware slop on the internet with machine learning, so the detection engineers and cyber experts could focus on the hard stuff. And for me personally, it took me a long time to sort of arrive there. Once we did arrive there, we made a lot of progress. So for example, Konstantin and I, who's sitting in the audience there, built this neural network that detects PE malware. In its final form, it was trained on more than 1 billion examples. We used VirusTotal to sort of noisily label the examples. And we didn't try to detect like the advanced nation state malware that definitionally operates out of distribution. We tried to detect like the mass, like spray and pray type stuff. And our company sold for $100 million thanks to this one neural network model that was, at the time we trained it, I think it was like sort of a side project. We didn't have very much equity in the company, and so we're not rich, but but it was a satisfying research result. And once we did that, we sort of rinsed and repeated this model of detecting the sort of mass, sort of like low tier, 80% of cyber attacks. So we built this convolutional neural net that detects malicious URLs, file paths, and registry keys. And this also shipped. Both the PE model and this model are probably protecting 100 million endpoints now. These are actually successful and actually useful. We trained a model. Actually, Konstantin, Rich, myself, and a few others who are in the audience here did this HTML, JavaScript, and CSS detector that detects like phishing pages and scam and fraud type pages. This also shipped and is actually having an impact. But again, with the same playbook where we had tons of training data, we were operating on a relatively stable distribution and weren't trying to solve the really hard problems. We were trying to make life easier for the experts who did the detection engineering for those harder problems. I mean, I think in full humility, like given that we now have the perspective that comes from having some distance from that decade, and we can say that I think successful deep learning models in that era were really sort of numerical signature databases. So they did a better job of writing like the low-hanging fruit signatures that you needed to detect cyber attacks. And we could have gotten there faster, I think, had we been much more sort of sober and evidence-driven and stuck to that loop in which we sort of looked at the evidence, oriented towards what was working, decided in a really selective way what to work on, and took action. And once this happened, I mean, this work, I mean, I was part of a community with Hiram and a bunch of others, who were all sort of coming to places like CAMLIS and exchanging ideas and sort of and building on the ideas that were actually working, which was a great experience. Okay, so I think this last decade was really a dress rehearsal because, for those of us in this community, AI security has been a very important thing for a long time. The rest of the world is just finding out about it. Like when I live in Kansas, and when I go to like a bar or a restaurant, and talk to the bartender, it's like they just found out about AI last year, and it's like there's a kind of new beginning happening right now, and I think that downstream of this is an enormous social transformation due to AI. And the question is, how do we put it on a secure foundation now? And I think this last decade was really a dress rehearsal for that. Okay. Just let the dopamine wash over you, and look at this kitten with this cute little bird. the evolution, it's not plausible in terms of evolution that they'd be friends. But okay. Any questions or discussion before I go on to the last part of the talk? I also am trying to remember how much time do I have? Okay. Okay. Okay, sounds good. Any questions or comments thus far? Please go ahead, John. Yeah. I think they'll be posted. Oh, sorry. The question is, will I share the slides? And yes. Oh, yeah. So just a filtered version where we just look at the kittens. Okay, yeah. There'll be two versions of the slides: one kittens only, and one with actual technical content. Any other comments or questions? Good. Yeah. So the question is, has the private sector moved beyond crystal balls to tarot cards? Oh gosh, just thinking about this. Yeah, I think so. I mean, I haven't seen as bombastic, of claims, like post ChatGPT as I saw last decades. But I think also that we're still figuring out how to make LLMs useful. So I think right now, like we're in the explore phase more than the exploit phase. I mean, I think that's part of the story that I was trying to tell just now is like there was an explore phase and we were sort of drunk on hype in many ways and probably didn't explore it as efficiently as we should have. But then there was an exploit phase where we sort of figured out what was working and actually cashed in on all the research investment. I think we're definitely in the first phase right now. Yeah, I guess that would be my answer. Okay. Oh, yeah. Please, one last question, then we'll go on.
Really enjoying it so far. I have a question about how maybe an more optimistic way of phrasing what you've been saying, which is, in a sense, right? AI is a history of being surprised. And so in a sense, yes, for a number of these research projects, like had we been more clear-headed to start, we would have realized this was not a great idea. But in a sense, right, DARPA and NSF, but DARPA specifically, are there to try a bunch of really crazy ideas, because every once in a while, we are super surprised with the result that is a lot more fantastic than we initially thought. So I don't know if there's I hear what you're saying. Maybe there's a more optimistic way of looking at like 2 years of research that didn't pay off, but like now we know it doesn't work,
Right.
like.
Yeah, that's a good comment. Yeah, I was a little bit worried that my narrative was too negative, and I think that's a good corrective. Yeah, I mean, trying to think about how to answer that. I do think that I do think you're right. I think like we're both right. Maybe like I think that it's very important to try risky research, but we also don't want to be inebriated, like when we choose what to invest in, and so yeah, I feel like that there was a fair bit, like I just remember going to a lot of meetings in that era, like with funding agencies where the program officer wanted like literally like AI to predict what was going to happen in the Middle East next year and this kind of thing. You know what I mean? And then but like when there's someone with funding who has a demand for that kind of research, there'll be lots of research contractors who show up who are willing to supply the labor. And there was like a fair bit of that, I would say, in the last decades. So there's a difference between risky research and like sort of fundamentally misguided research. Yeah, and like what I was trying to do is like implicate myself in some of that because I feel like some of the investments we made could have been calibrated slightly differently, But absolutely, we need to take big risks also. So I don't know. I think those are both true at the same time. Yeah, but thanks. That's a good comment. Okay, I'm going to keep going because there's a bunch more stuff in here. Okay, so here are some like foggy areas where I think we need to like operate this algorithm where we're gathering evidence and not fooling ourselves and taking the next step. Oh, that's too bad. I don't know why there's no animation here because I can't show the material. I don't know if there's any way to fix this. There's like some material. Unfortunately, like a lot of material will get occluded here because it's not like animating the stuff in. I'll start talking about this and just give the general idea. So, okay, I think LLMs are so the current hype in the LLM space is around getting LLMs to behave agentically and to plan and reason. And this is like a very confusing domain that I think we're gonna have to figure out as a community through a lot of research and empirical testing. And here's why. So large language models. So imagine you could see a bar chart underneath. This is the thing. So like Llama 3 was pre-trained on 15 trillion tokens. So that's so imagine a bar showing that, and then imagine a bar with actually no pixel space at all, showing the number of words that a human reads in their lifetime. There's a huge contrast between what Llama has seen and what we can even imagine any sort of cognitive object witnessing. And that's a big problem for figuring out where LLMs can plan and reason, because you never know if the LLM had just memorized it. So if you ask an LLM to solve a hard planning problem, you don't really know if there's data in its distribution, in its training distribution that's quite similar to the problem or not. So it's almost impossible to know whether the LLM is really generalizing in many settings. And this is really hard, and I think probably some of us have been down the path of thinking, oh, I can use an LLM to automate this process because I played around with it a bunch of times and it felt like it was reasoning. And then you actually go and try to land some actual impact with the LLM, and it completely falls apart. And that's probably because you were initially playing in distribution and now you're out of distribution. At the same time, we know that we know thanks to neural scaling laws that LLMs get more data efficient the more we train them and scale them. And they actually do generalize to some degree. And the level of generalization is remarkable, right? I mean, I can come up with some gobbledygook and have it that it's definitely never seen in its training distribution, and have it translated, to Spanish, and it does it correctly, right? So it actually has learned some sort of general functions that really are abstracted from the training data. And I think there's just going to be a lot of experimentation we need to do to figure out where LLMs can plan and reason. And that'll have to be continuous as the LLMs get better, because they've gotten they get dramatically better with every new model launch. Okay, here's another included slides. Okay, I'll just talk to this. So in 2025, I think we'll see lots of new large language models launch with much better reasoning capabilities. So this slide has a chart from a paper that came out of Meta, showing how you can use reinforcement learning with Llama to train Llama to take 50 to 100 steps in a programming environment and do dramatically better at solving programming problems if you give it reinforcement, if you give it a reward function from a software engineering environment. And imagine a plot on the right showing a massive step function in software engineering capability with Llama, thanks to this reinforcement learning procedure. We're actually currently, Lauren and I, who work together at Meta, Lauren's currently trying to fix the PowerPoint, are currently working on an experiment where we're applying this reinforcement learning methods to bug fixing. So we have a huge backlog of bugs at Meta, like security vulnerabilities that need to be fixed. And it stands to reason, right, if you have a good reward model where you can run a proposed fix through a CI/CD pipeline and make sure that a fuzzer crash doesn't reproduce, that you can use reinforcement learning to train a large language model to do much better at fixing bugs, even when it's taking lots of steps in an agentic workflow. And so we're going to find out, right, if this works well in the next few weeks as we do our experiments. But I think this is just an area where we don't know, right? And you can imagine that reinforcement learning is this kind of reinforcement learning design pattern is going to generalize to a huge number of problems in cybersecurity. For example, pen testing, right? I mean, you can imagine constructing a really good simulated environment where you put an LLM in an agentic workflow and have a reward function at the very end of a kill chain. And that LLM, when you train it at scale, suddenly becomes, an almost, sentient feeling, red teamer, or maybe that won't work at all, So this is one foggy area that I think we'll have to figure out as a community while sort of doing the kind of loop that I'm advocating for. Oh, okay, this slide is not included. So how many people have been following inference scaling laws? Anybody? Okay, so how many people know about neural scaling laws? Probably, okay, so some of us. Okay, so let me explain these really quickly. And I think maybe somebody here remembers, I think in 2020, a paper came out from Jared Kaplan that described how neural scaling laws work at training time. And so basically what these scaling laws show you is that as you vary a few design parameters, like the number of parameters in your neural network, the amount of training data, and the amount of training flops you invest in the neural network, validation loss on next token prediction can be predicted with like a really clean regression function. So basically, there's like a power law relationship between these design parameters and the error rate of your LLM. And as you scale the sort of punchline here is that as you scale neural networks up in training and in compute and parameter size, they it looks like you guys fixed it, yeah? Or okay. 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 Gotcha. I assumed it was a PDF. Yeah. Yeah, there are. Yeah, yeah. Okay. Yeah. Well, I can keep talking, or we can keep showing the cat. I mean, like, you can show the cat while I talk. Also, I mean, it's best of both.
Say the word, and we'll switch it.
Okay. Yeah. Yeah. You can switch it. Hmm. Yeah. Yeah. I know. Well, I'll just finish what I was saying about neural scale. So the basic idea is that at training time, like as you scale the neural networks up, they get better. In the last year or so, there's a kind of a new thing going on where we've discovered that you can invest more inference time compute. So after the model has been trained, and there's like at least in many problem domains, there's like a clean relationship between like inference compute and the goodness of your results. So for example, in the simplest case, in solving, say, competitive programming challenges, as you scale the number of attempts you give the large language model to solve a competitive programming challenge up, like there's a log linear relationship between how many attempts you give the neural network and okay, here we go, and its probability of success. That applies to math also, and it really seems to apply to most contexts in which you have the following setup. You have an LLM that can propose a solution, and then you have some deterministic method that can verify the solution. And I think this is really interesting because what it suggests is that you can take a model like Llama 7DB and just try it a bunch of times in the simplest case. And if you have a verifier, you'll eventually get a valid solution. So for example, in like the auto bug fixing setting, right, this might be a useful paradigm. I guess it's sort of obvious, but it's useful to recognize because it might open up a bunch of use cases where in security we want to try things a bunch of times and verify them. And in a more advanced setting, you use reinforcement learning to take the cases where the LLM was successful and then retrain the model based on those cases. I guess my punchline on this slide is just that I think we still don't know as a field where inference scaling laws are gonna matter. So I think it's really up to this community to figure that out, in a kind of iterative evidence-based loop. I think adversarial examples are really interesting. How many people read the original Ian Goodfellow paper on fast gradient sign? And okay, so many of us have been part of this discourse or have followed it. So the basic idea behind adversarial examples for those who are new to this in deep learning is that you can use the same kind of math that we use to train neural networks to create examples that fool neural networks. So in this famous paper from Ian Goodfellow, what they did is they took an image classifier and took an image of a pig, right, ran it through a neural network, and decided they would like the neural network to actually see this pig as an airliner. And so they backpropagated through the neural network to figure out what the gradients would be to maximize the probability of airliner. And it turns out there's just like a small perturbation you can add to the image that will get the neural network to think that the pig is an airliner. Imperceptible to the human eye, but that totally tricks the neural network into thinking it's looking at an airliner. And so there was a whole literature on this for a decade on creating new adversarial example techniques that fooled neural networks and then defending against those. At Meta, we had a team focused on combating adversarial examples, but they never actually observed any adversarial examples in the wilds trying to fool our classifiers. So that's interesting, right? That an academic community was sort of focused on this problem domain, but we never saw it show up in the wilds. So it feels like maybe this area is dead, but maybe not, right? Because now we're putting AI models in charge of all sorts of crazy stuff like operating systems and software engineering processes, and maybe adversarial examples will start to matter much more. I think this is an open question, and I'm curious about the sort of real world implications of this. I think this is another thing we'll have to figure out as a community. Maybe folks disagree about what I just said about adversarial. Maybe there were cases where they showed up in the wild. I personally haven't observed them and would love to. Okay, looks like I've got a few disagreements here. So I'll wait till the end and we can talk about them. Okay, so okay, and so there's another area that feels totally open and unclear to me, which is prompt injection. So prompt injection is something that we work on Lauren and my team at Meta. And that I think we're nowhere close to converging on like a good solution to right now. How many people know what prompt injection is? Okay, like almost, okay, looks like everybody knows what prompt injection. Okay, so like, this is an interesting problem because it's so intrinsic to the way this new technology works. And also because we're putting large language models at the center of operating systems and office applications and social media, and giving it a lot of autonomy and power. So this diagram on the right is a kind of architecture diagram for Microsoft Copilot. And you see the large language model over there on the right. Here, let me see if I can get this thing to, oh, there we go. Okay, so here's the large language model. The large language model has access to the Microsoft graph, so emails, files, meetings, chats, calendars, lots of sources of untrusted data and also sensitive data. Has access to plugins probably from third parties, and who knows what those do. And this whole system, I mean, now there's been actual CVEs that have been filed against Microsoft Copilot, showing that there are real prompt injection risks here that can lead to betraying confidential data in the face of a prompt injection. How we mitigate this, I think, is a really open question. How we balance between the value proposition of AI and offering, autonomy and automation relative to prompt injection risk is unclear. Like the strength of our interventions, like right now, Lauren and I work on like a firewall product that sort of monitors all the interactions between LLM applications at Meta and applications and sort of looks for prompt injection attacks. That's a pretty lightweight intervention. You could go much further and implement like a taint analysis system where we're tracking, whether the context window of an LLM is tainted by untrusted data and forcing some deterministic controls at that point. I'm not sure what the right sort of level of heaviness is of this intervention. I think this is something that we'll just have to figure out, and hopefully 5 years from now we'll be at CAMLIS and have a much more mature sort of perspective on this. Okay, I'm gonna go quickly through the last few slides to leave room for discussion. So stuff that we're working on at Meta. So we've done a bunch of work over the last year around sort of accumulating evidence around large language model security risks. So we've developed a framework called CyberSec Eval, which has 8 different evaluation suites that measure various properties of an LLM. So like prompt injection susceptibility, cyber attack capabilities to look at how helpful an LLM could be to cyber attackers, propensity of an LLM to generate insecure code. And the idea here is to have evals that we can repeatedly run every time we go to release a llama model to understand security risks, and then we work on mitigating them by fine-tuning llama models before they go out the door and that kind of thing. These papers are all public. If you look on Google Scholar and search for CyberSec Eval, you can find this work there. Here's an example of how I think being open and grounded in evidence really helps. So one of the evaluation suites in CyberSec Eval contains like simple toy programs that are exploitable. And the way the evaluation works is we asked an LLM to exploit the program. So we developed these evals, I don't know, I think in February with one of the Llama launches. And we found that Llama did a terrible job at exploiting these programs. And my assumption was that, well, LLMs can't really reason about programs, and that's why they're failing. But then a team, a sort of sister team at Google Project Zero took CyberSec Eval, because we open sourced it, And they built a sort of agentic framework around cybersec eval, and they actually saturated a bunch of our exploit benchmarks and showed that LLMs could indeed solve many of our exploit challenges, which is interesting. So, I had to update my beliefs about, LLM's ability to plan and reason in the program analysis domain. Here's just a few things about how we're approaching prompt injection risks. In the interest of leaving some time for discussion, I'll skip over these since I sort of talked about that already. I mentioned we're working on this reinforcement learning from execution feedback experiment. We're really interested in seeing how reinforcement learning, when we're computing a reward function in the context of automatic bug fixing, can help automatically fix bugs. And then we're doing a lot of table stakes work. So people are welcome to come talk to me about this after, around applying LLMs to like threat modeling, to generating reports internal to our security department. We use LLMs a lot in threat hunting within our internal security operations center. We use LLMs probably in the same ways that many of us in this room are using them in these sort of bread and butter cases. And we find there's lots of incremental efficiencies in these kinds of applications. Okay, so that's this AI security surprise monster that I started with. Just summing up. So I think our basic dilemma in this field is that we're the beginning of, I think, a transformation of the tech industry and probably society due to AI. I think our field is incredibly important. I think the decisions we make in this community right now are going to be incredibly consequential 10, 20, 30 years down the line, because we're establishing precedents and norms and technical approaches and platforms that are going to shape the way AI security works, and yet we don't know exactly what to do. And so I think that we need to stick very closely to evidence. We need to be willing to update our priors very quickly when evidence contradicts them. I think it's very easy to fool ourselves given all the noise right now around AI. And so I think it's important to be intentional and disciplined around not doing that, and then just continue to take the next small step. And if it's not those of us here at CAMLIS, I don't know who it'll be. So the implications of this for our work, it's really up to this community to provide clear and unbiased signals to our industry, policymakers, and leaders. Like, those of us in this room are the experts in this field, right? It's up to us to speak up, even to power, even to those with fancier titles than us in our organizations. There's a dearth of good empirical evaluations in security, so I would really pitch building evaluations that ground discussions on an empirical basis, like cybersec eval, but there's probably lots of other evaluations that we should be building. Building a cross-industry technical culture, like what we're doing here, I think is absolutely fundamental. I think that we absolutely cannot succeed if we're siloed, within small teams, within larger organizations. We have a shot to make a huge difference. Okay, that's it. So thanks a lot, everybody. And yeah, I really appreciate you guys inviting me.
Thank you, Josh. We've all been part of a classic now. So we have some questions online. We have some questions in the audience. We need to wrap up our discussion in 5 to 10 minutes for our break.
Hey, I asked this online too, so we'll get 2 for 1. So you think you touched on a little bit. I posed the question in the chat, like thinking about those last 10 years, which was therapeutic. Thank you. The progress, looking at something like Ember, or even some of the talks about malware yesterday, I feel like a lot of the progress in the 2010s followed some of the shared data sets and benchmarks that we were able to sort of share as a community. You mentioned one of the last points you made was sort of like, if we stay as siloed communities within large organizations, some of that collaboration and sort of fool yourself checking that you mentioned, hey, Google did this and that helped me realize that maybe I've changed my understanding. What do you think those areas are moving forward? What are those areas for, one, do you agree with that the sharing is what helps us stay grounded? And 2, where can we share in the future, if beyond just malware samples and malicious URLs?
Yeah, thanks. It's a great question. I don't know if I have a great answer. Yeah, just thinking about this. So yeah, I think that so I'm just repeating myself a little bit, but it's possible the analog to data sets like Ember and Sorrel is our LLM security evals. We've got a small team at Meta building cybersec eval, and there's no way we're going to do that job on our own. So I think, yeah, I mean, there's like a huge space to cover in building like the value of LLM evals is that they're repeatable. You can compare models, you know, at a point in time. You know, like we compare, like when we run CyberSec eval internally for llama models, we compare against all our competitor models in the industry. But then you can also compare across time to track progress and see if there's an accelerating trend or deceleration. You know, there's like that's, I think it's a useful signal there too. And there's like lots of, like, CyberSec eval covers a tiny portion of the overall space that we might want to cover in this community and around tracking progress. As we all know, right, benchmarks also incentivize progress. So, you know, machine learning did really well on ImageNet, partly because of ImageNet, you know, and I think that's the case for, you know, that's the case for SWE-bench and all the big, you know, benchmarks that are out there that are sort of driving progress. So we have an opportunity to shape things. Like one of my, like, full disclosure, one of my strategies within Meta is to build CyberSec eval to try to influence the larger llama community to maximize or minimize the metrics that we care about. So I think that's a big one. Yeah, in terms of like breaks in the grass where we could fool ourselves, I'm not sure I can identify any ones in particular. I just know that there are still, at least in my job, that like, you know, our VP will say like, okay, you guys should figure out how we're going to maximize efficiency using AI, which is like using AI, which is like a totally reasonable request, you know. But there's like a pressure to like, I don't know, how do I put this? There's a lot of people coming in offering funding and headcount and this kind of thing for generative AI. And I think it's just important to speak truth to power around like where it actually makes sense. But I'm not sure. Yeah, I think it's up to everybody in this room to figure out where it actually does make sense. Yeah.
Thanks.
Yeah.
On specific evals, like 8 is a lot in CyberSec eval. What are additional evals that you want to see built, or like what are shortcomings of the existing ones that you would like to address first? Yeah, I'm just curious about like what else you think people should do first.
Yeah, that's a good question. For other people here have answers also. Lauren, if you have any thoughts, you're welcome to chime in. Lauren is tech lead for CyberSec eval, so yeah.
Okay, all right.
Yeah.
Yeah, I mean, I think we chatted a little bit about this yesterday. Like one of the big shortcomings is kind of related to the example Josh gave in terms of like for the cases where we're trying to actually measure offensive capabilities, right? There's a big difference between what a model can do when you just prompt the vanilla model and say like, hey, go hack this network, versus if you enable it with a bunch of specific cybersecurity tools and maybe embed it within an agentic framework where there's specific specialized agents that can do things. And so, yeah, that's kind of what the Google Project Zero thing showed for the exploitation test specifically, but I think it applies more broadly. So I think that's one thing is figuring out, and it's not a straightforward problem at all, right? Like figuring out what the proper like model under test should be to accurately reflect what it is we actually care about. And then I think in terms of like other like new spaces that aren't covered at all, I think a big one that's coming that we've been talking a lot about is as models increasingly take in more modalities of inputs and outputs, you know, like it's very difficult to keep up with creating benchmarks that cover all the possible ways in which an adversary could exploit these things. So I think we have to do a lot of like threat ideation to figure out kind of what makes sense and imagine like what we need to test for. But at the same time, we need to not confine ourselves to our like, you know, potentially very wrong like priors about what these threat vectors are. So like in the case of multimodal inputs, for example, we've been thinking a lot about like where injections are likely to come in and like which should be kind of like the higher priority channel for instructions that the model is expecting and which ones are more likely to contain data. And I think like I can think through like various product uses of like models that have all these different modality inputs. But I know that I can't think of all of them. And that's kind of like what's so exciting about the field, right? Like I have no idea what people are going to do with these things. And so we have to find a balance between trying to stay realistic about like trying to develop benchmarks that measure what we actually care about, but also not too restrictive in assuming that what we care about is kind of just like what we can imagine right now.
Yeah, that was awesome. Thanks.
If I may, real quick, Young, I'll take a question from online. One I think really great question was, I think in reference to the inference scaling laws. Do you think that there are implications here for red teaming or assessment work that would suggest that we need to be more careful in how we're doing these assessments, given that models, can get it right, maybe not the first 20 times, but the 30.
Yeah, I think that's a great question. I think I think there's big implications there. Like the assessment problem is, so this is one example of why the assessment problem is so hard. Like, so when we started doing cybersec eval, we weren't thinking about inference scaling laws. When we released Llama 405B, which probably some of you guys know about, this is like our most capable model. It's sort of roughly on par with GPT-4 in July. We did a ton of assessment because we were open sourcing a very powerful model, but we didn't consider inference scaling laws. And then we released Llama 405B, and possibly adversaries will use, the inference scaling laws concepts, with that model, and use that to find vulnerabilities in codes, or in some other setting in which that makes sense. So that's just one example of how difficult the evaluation problem is, and how approximate it basically always is. So yeah, we should be considering inference scaling laws when we consider the uplift to adversaries that we'll be providing when we release one of these models. But there's probably a bunch of other things, like I think that Lauren touched on also, that we should be considering too, like their use of like very advanced tool augmentation and retrieval augmented generation. Their very high level investments possibly in agentic frameworks. It's very hard to simulate all the things, or to sort of extrapolate out to all the things. So this is always going to be an uncertain domain, which is part of why I'm pitching other people. Eval is being a community effort and not just the property of one company.
And I've heard you say, Josh, imitation is the greatest form of flattery, and I've adopted this phrase from you that LLMs in particular have made AI load-bearing in our software today. And I'm interested in your comments on what the ramifications are for ensuring security of these applications now that they're not, they're not becoming replaceable parts, or is that not optional?
Yeah. Well, yeah. Thanks, Hiram. Yeah, I mean, I think there's probably many of us in here who work on AI and application security, right? And like, I think that the fundamental tension there is that for AI to realize its promise, the promise of AI is that it can automate the work that we do manually. But to realize that promise, we just have to expose it to prompt injection risk, I think. So for example, I can't even have an LLM go out and do a bunch of research about what hotels I should visit on a trip to Italy, without also just necessarily introducing prompt injection risk that can't be 100% mitigated based on the current fundamental principles of the technology, right? I mean, like the only deterministic mitigation to that problem of having an AI agent go do research on what hotels I should stay in, and would be to have like an enormous number of annoying confirmations, where I'm like confirming that I'm okay having the LLM process data from this URL, or basically it would become unusable, So like that's a simple case, right? But what happens when you have the LLM, integrated like Microsoft Copilot into the engine room of the operating system, and give it the power to send emails, and organize a birthday party for your kid where it's like looking at your social graph and sending emails. Yeah, so I think I'm just reiterating what I guess your question, Hiram. But like, yeah, those are all cases where you can imagine if AI is successful and gets widely adopted, it's like load bearing in our everyday life. But there are like the fundamental science suggests there's no real like deterministic solution to the security problems. So this is why our field is exciting, right? Like hopefully in the next 5 CAMLIS conferences we'll make progress on solving this problem. But I don't have any good answers. So yeah.
We have time for maybe one more.
So I'm going to build on that and maybe kind of feed your own words back to you a little bit.
Yeah.
We'll observe that we're putting AI everywhere. We'll observe that we have no good mitigations, like you point out, for prompt injection. So let's orient to that And now how do we decide and act? Like, what do we, in a world where we can't mitigate prompt injection effectively, but we're still putting LLMs into more and more complex applications, more and more agentic sort of like self-driving workflows. What is it that you think we should be looking at as a potential solution, mitigation, control to sort of balance out this utility versus vulnerability question?
Yeah, well, I can tell you what thanks, Rich. That's a good question. Well, I can talk about what we're currently doing at Meta. And I hope well, so yeah, I'll just describe what we're doing right now. So a number of things. So one, we're measuring in CyberSec eval the propensity of llama models, which those are the only models we use internally, to succumb to a prompt injection. We've got some work starting around fine-tuning the models to be more resilient. We have a whole application security practice around working with product teams to refrain from using LLMs where it's like clearly not safe, or to add in confirmations and this kind of thing. You want the LLM to ask before it makes a purchase with your credit card, those kinds of things, right? So we're doing traditional sort of application security sort of work like that, like all the obvious things that you would do. And then we have a firewall platform internally that sits in. It's probably very much like what other people here are doing, but it sits in between all of our applications at Meta that use LLMs and the LLM platform, and we monitor all that traffic. And that part, I think, that part of the practice it's interesting to look at in historical context because. Basically what we're doing there is like for the residual risks that we couldn't mitigate with all those other interventions, we just monitor all the traffic and we have detection funnels that detect and block bad observations. That looks very much like malware detection pipelines, actually, right? So like what we built with like Windows, with all of the OS platforms, are these very open platforms where you can just load an ELF or PE onto your system and just run it. And people can do that in an enterprise. And oftentimes those, too often those are malware, and so the mitigation we built as a community to that are these sort of firewall, endpoint security platforms that have no deterministic guarantees, right? They just work some of the time, and they mitigate the risk. And I think we've gotten to a steady state in which the risk is acceptable, and we still run those platforms. I guess it's a big question, right? Is that the direction we're going to go in our community against this risk, or are we going to find, or are we going to do it better this time? And I'm not sure. Yeah. Hopefully that was a helpful response, Rich. But yeah.
There's certainly more discussion to be had. We're unfortunately out of time. There's for those who are listening, there's a great discussion happening in Slack that Josh's remarks have instigated, including this small, discussion about are there adversarial examples in the wild?
I'd love to see the response to that.
The whole therapy session that we've been on today and doubting our past. So let's thank our keynote speaker one more time. Thank you, Josh.